So what happens in the mechanism is, for the basic hydrolysis, the nucleophile is the very strong hydroxide. It attacks the electron deficient carbon, that's delta positive, break the pi bond here, it goes back to form the imine anion. After that, you have some kind of equilibrium with the water, and then it picks up the H to form the imine. Alright, and then after that, it will undergo some, what we call tautomerism, tautoma, no? Sounds like an ox, right? Yeah, to form an amide first, and after that gets hydrolyzed again by the same hydroxide, and then you get the carboxylate, and then finally you acidify it, you get back the corresponding carboxylic acid. And then, alright, so if you do a partial hydrolysis of a nitrile, you can get the amide first and then you get a carboxylic acid, but sometimes it's very hard to stop here because it's difficult for us to control the reaction and say, okay, stop, don't move, freeze, don't go to the carboxylic acid form. We can't, because the reaction is ongoing. Even when we stop it, sometimes you just run away and they don't wait for us, like some of the buses. Experienced before? So this is the arrow pushing, what you could know about in a microscopic level of how the ions and the molecules interact, bond forming, bond breaking, and finally give you the product. Now for the acid catalysis, hydrolysis, we know that water is a weak nucleophile, so it's not able to attack the carbon that's delta plus, even though it wants electrons. So what happens is the acid H plus will be picked up by the nitrogen of the CN group. So now we have the N plus, which makes the carbonics to be even more electron deficient, and then the water, which is a weak nucleophile, is able to attack the carbon, because now this wants electrons so bad, so it doesn't care what kind of nucleophile it has around it. Weak one, strong one, just come attack me, okay? I warn you. And then slowly it forms the imine, and after that forms the amide after doing the tautomerism, and of course gets hydrolyzed by the water again after picking up the H plus. The same story goes, undergoes exchange of H plus, and finally you get the carboxylic acid. So you see a pattern is, when you have an acid catalyzed reaction, right, it's always something that picks up the acid first, makes a positive charge, and then the water or some other nucleophile will attack the atom adjacent to the positive charge atom, break the pi bond, and then after that slowly move your H plus again, move about, and the same story goes. You see here it was okay, and then now this guy picks up the H plus again, right? Then water goes and attack the atom adjacent to the plus charge. Same old story. See a pattern here. This is organic chemistry. Try to map your ideas across to another example, you will do well. Now we could also make carboxylic acid using the Grignard reaction method. So what happens is, right, we use a Grignard reagent. Here we are using the phenol magnesium bromide, and the electrophile here is CO2, dry ice, okay, solid carbon dioxide. So we see a delta plus carbon because it's next to 2 electronegative oxygen, and the C minus here will attack this carbon and push, and you get the carboxylate. And after that you add an acid to do an acid-base reaction, you get your benzoic acid. This is what we did in the synthesis of ibuprofen in level 3 chemistry major. Now notice there are complementary synthesis routes. From benzyl bromide, we could actually use sodium cyanide as a nucleophile to convert it and step up the number of carbons in the whole molecule, and then do hydrolysis, we get the phenylacetic acid. Or we can add Mg ether as a solvent, then we form the Grignard reagent, we add dry ice, and then acid, we get the same product. So in organic chem, it's very good for you to think about the different ways to arrive to the same compound from the same starting material, but different intermediates, different reagents used. Challenge yourself, practice more. It will be useful. Now for nitriles, right, they exhibit similar chemistry to the carboxylic acid because both have a carbon atom with 3 bonds to an electronegative atom containing the pi bond. another mouthful. So basically, you see delta plus, delta minus, pi bond. Delta plus, delta minus, pi bond. This is what the sentence was trying to tell you. That's it. So this carbon here that's having a delta plus, they are strongly electrophilic. They want electrons. So how do we prepare nitriles in the lab? Remember, back in your halogen alkane series, we learned that cyanide is one of the best nucleophile that you ever learned. So we do a reflux of a sodium cyanide or potassium cyanide with an alkyl halide or halogen alkane to get the product. SN2. Very good. Now for the nitriles reactions, they could be hydrolyzed into carboxylic acid. You can refer to slide 8 and 10. Reduction of nitrile using lithium aluminum hydride, a very strong reducing agent. You would get the amine, right? It's an amine now, which is basic. This is the mechanism, right? What happens inside there? But just know that when you reduce it, these two combine, you get the amine form. You just pump H inside there. Or we can do a reduction of nitrile using the Grignard reagent to give the corresponding imine. You don't stay here, you move to become a ketone. So nitrile and Grignard give you ketone. Okay, go with this pathway and it's easier to go inside your brain. So benzonitrile, Grignard reagent, you just pump this blue chunk into the carbon here, and then the end becomes the double bond O. Simple as that. Propion phenol. So that's all for this topic. I'll see you next time. Good night.
You're the light, you're the night, you're the color of my blood. You're the cure, you're the pain, you're the only thing I wanna touch. Never knew that it could mean so much, so much.